Well, CommonJS in brief is a sort of strange confluence of people whose name starts with K and are Kris. I think there are 3 of us. It's really weird. But there's Kris Zipe and Chris Walker and me, which makes the mailing list a bit confusing. But which brings me to the point, CommonJS is a mailing list and a wiki. And our charter is to develop specifications for JavaScript ad hoc from the grassroots for contexts on the browser and outside of the browser and beyond. We started about 2 years ago by Kevin Dangor with a blog post, and our first thing that we did was we constructed a module spec, which was probably most noted because Node implemented it pretty quickly on, and is certainly the widest deployment of it. But not the only. There's also Narwhal, Gypsy, whole bunch of server-side embeddings also in the browser by a few. So the purpose for the group originally, the last year has been really quiet for CommonJS. The group was originally started because there were a whole bunch of server-side JavaScript frameworks that were not really taking off, and Kevin's theory at the time was that the reason they weren't taking off was because it was kind of pointless to write JavaScript for any single one of these somewhat crappy platforms. Because you really couldn't, there was no escape route. You couldn't go to a better system if you could, if you found one. There was no degree of interoperability. You just have to rewrite it every time you move to a new platform. So he started the group to work on some of the basic standards that we would need for server-side and systems programming. Things like a module as a basis for everything, packaging, binary data, file systems, and I/O. So we worked pretty hard the first year to get the file systems and binary and stuff like that worked out, but we were kind of going the wrong direction, and Node sort of proved out that we really need to look into asynchronous file systems and I/O before we start writing, and actually get some asynchronous implementations in JavaScript before we start standardizing them. And it was an easy trap to fall into because there are so many well-vetted synchronous file system APIs on the server. We figured it's pretty well-researched prior art, and so we just took those and found the best things of them and tried to make the very best synchronous file system API that there could ever be and put it in JavaScript. And I think that a lot of that work is still useful at this point, but I'll get to that about promises in the second half of the presentation. But yeah, so the actual problem turned out to be that there weren't any JavaScript server-side implementations that were interesting enough to use that could differentiate themselves from other programming languages and implementation languages on the server side. And the last year has really proven that out. So what makes a good spec? What are the things that CommonJS should be talking about and standardizing? That's a pretty common question we get. For the last year, we've really stepped back and let things happen in the foreground, and we've just focused on some very core proposals. But the charter is very much the same. We still need to get out there and have specs for the whole spectrum of things, so that there still can be an escape route and a degree of interoperability to the sense that it makes sense for there to be interoperability. Like if you have a package of code that has absolutely no dependence on I/O, it makes sense for there to be like a markdown package that just works in the browser and works in the client and no difference. So. Yeah, so working it in that way. So what makes a good specification is, and there has to be compelling reasons to write a spec, because it's 10 times harder to write a spec and get a whole bunch of people to agree on it, and it's not nearly as fun as hacking. Arguing with people is a real pain. So it really has to be worthwhile, and what makes a spec worthwhile is if it builds a new ecosystem where a whole bunch of code can be written to be interoperable. Modules was a very obvious place for that. Basic asynchronous I/O, like basic asynchronous programming constructs are another big one. That area hasn't settled. So what makes a bad specification is specifying something that people don't agree on in the first place, and there's a lot of room for experimentation. So Modules is sort of done-ish, and then we're moving on to packages. Packages are the next big thing that makes sense for CommonJS for building new ecosystems of stuff. So we have a stopgap proposal for packages called 1.0. This proposal doesn't really define any behavioral requirements. It's sort of like, I don't know if you've ever, in America we have the Liberty Bell. It's this gigantic bell that had a crack in it really early on and just kept on getting worse every winter. And they drilled a little hole at the end of the crack to relieve the pressure so that the crack wouldn't grow anymore. Packages 1.0 is sort of like that and less about actually guaranteeing any degree of interoperability with packages. In the Skywriter talk upstairs, they talked about just being able to grab a CommonJS package and use it on the browser. And the fact of the matter is that at the moment there are packages for Narwhal, there are packages for NPM, and there are packages for Jetpack and Skywriter, and none of them are actually interoperable, but they do have the packages 1.0 in common, which prevents them from diverging too much away from eventually being able to specify their dependencies in a meaningful way. The packages spec just reserves a bunch of names for things, for metadata about packages, so that eventually we can have an ecosystem that can analyze that data and use it for installers and stuff like that. But Michael Rogers has been pushing for the last year on new packaging spec, and there are 3 major proposals for extending packages for handling dependencies. One of them is approached by NPM for Node by Isaac Schluter. There's another, I wrote one 2 years ago for Narwhal called Tusk, and it had a repository format as well. And then which is based off of this concept of overlays. And then there's a third method that's being presently promoted by Kris and is embodied and implemented through this node package called nodules. So there are three major approaches. There's overlays, mappings, and linking by version through a registry. And none of them are really perfect, and we still have a lot of room to experiment with these things. Let me describe some of the problems and benefits of each of those approaches. The overlay approach is similar to Ruby. That's what we used in Narwhal and Tusk. And the way it works is that the package manager is responsible for installing your packages in predictable locations, and then Narwhal discovers all of those package locations upon initialization, which takes an unreasonable amount of time in Rhino anyway. And the way it works is that it goes into your main package directory and then does a breadth-first search of the packages directories of each package that is contained in that package transitively. It discovers all of those packages and then looks at its dependency mapping and does a topological sort, which linearizes all of the packages out and constructs a require paths array so that Narwhal knows where to search, which directories to search for each of the modules in all of the packages. The problem with this approach is that it conflates the module namespaces of all of the installed packages. And one of the advantages of the approach is that it really makes it easy to inject engine-specific code anywhere along the way. And it also makes a really great composition mechanism if you have something like Django apps in JavaScript, where you can have a media directory tree that can be searched for the most relevant stuff, and you can stack it on top of each other and override lesser versions of that information. So that's the Narwhal approach, and it's one. And NPM is the second one, really. And the way it works is that it creates symbolic links in a common directory. So the difference in approach is that Node does nothing at runtime to discover anything about packages. There's only a single directory that contains the entire module tree, or a small number of them in a fixed require paths. And the way it works is that the package manager is responsible for telling the entire system the names of every package and how to find them by using symbolic links. So, and thunk modules that alter the require paths as you call through require, which is a major disadvantage of the approach, is that require behaves differently when called in different turns of the event loop. So you really can't use that approach reliably when you have multiple versions of a particular package, and you're calling require at funny times, which has largely not been a problem for the Node community yet. I'm sorry?
It's not a problem because it requires state. So it basically shifts and pops into the array. So it's basically hierarchical. So it won't affect your package if you want a different version because you would not be inside of that.
So Michael points out that that because require is synchronous, during the context of the require call, your require.paths will be consistent. I'll think about that a little bit more. You just have to be very careful about anything where state is captured in your stack, because it tends to vary from turn to turn. The other disadvantage of this approach is that whenever you install a package, it establishes a race for naming packages. There's a gold rush for the good names going on in the Node community right now, and the collective consensus of everybody who's chosen a name is reserving names in every package's and every program's namespace effectively, which makes for unpredictable composition problems down the road, possibly. I really like the idea of having sovereignty at various layers of naming conventions, so that people in different roles have the ability to give names to things in their own scope, so they have absolute control. And one of I think of it as in a particular module, your local scope should be sovereign to you. You should not be subject to other people giving you other global variables from other modules. You should have absolute control over the local variables in your scope. Similarly, at the package layer, where people are composing pieces of larger chunks of code that have been produced by different developers, you want to have sovereignty over your module namespace, and ultimately you want to defer all of the responsibility for naming things to IANA or just to URLs in general, so that you don't have to mediate conflicts in naming by talking to people who have authority. You talk to get your domain and put it up. There's no conflict. But in any case, so those are the major three approaches, and we're still continuing experimentation with them. I imagine at this point that while it may seem like a design by committee sort of end result where you have little bits and pieces of each of these approaches, I think each of them has their own merits and disadvantages. So down the road, I imagine that the packaging approach that we ultimately use will be a hybrid of these approaches, where easy is simple and the long out problems are solvable. So that's packages. We also talked about binary. In the first year, we talked about binary in the context of making binary data types that resembled array and string, so that we could use genericity to our advantage, and also because there are good security properties of strings. You can give a string to somebody and it's guaranteed immutable by both the consumer and producer. So we have that layer of abstraction for strings. It also was made to accommodate older versions of browsers. The idea was that people, not browsers, but older JavaScript engines, the idea was that it could be implemented in pure JavaScript without involving the embedding, which made it slightly of compromise. We fast forward a year, Node has given us a buffer type, so I went and took that and codified it and made some changes and revised the design, and that's the binary F specification. So Node has essentially a CommonJS compliant buffer by virtue of being the inspiration of the spec, and everybody else has one now too. Now the neat thing about the binary specs is that we have this more abstract byte string and byte array specification, binary B, and we have the buffer specification. The more abstract one is easily implementable, even including possibly copy on write semantics in terms of the lower level buffer. The problem with buffer is there are a lot of problems with buffer if you ever introduced, if you ever tried to use Node in a secure way. As buffers they're never blanked out. on initialization because that would be a performance cost that Node doesn't want to make. But that means that if you have multiple distrusting parties running in the same process through JavaScript, which is a dream that is realizable through ECMAScript 5 and Harmony Forward, you won't be able to use buffers in those contexts because there would be potential of binary garbage data leaking into those contexts. So that's binary. But I really want to talk to you about promises today. There's a specification for promises long predating the entire CommonJS effort by a fellow Tyler Close for a project called refsend. And the Q API, as he called it, and we carry forward, is this really highly researched, very carefully thought out API for composing asynchronous programs in reliable ways in the face of hazards, distrust, and all sorts of other things. So it's a really robust way of dealing with asynchronicity. So let me show you what. I was going to talk about set exports. Don't have to do that. Or the module constructor. Or yeah, we can come back to that. This is a promise. So what a promise is a unidirectional communication channel between a producer and a consumer, possibly many producers, possibly many consumers. The way it works is that you construct via q.defer a deferred. A deferred is an object that contains a resolver and a promise, and they're separate for a reason. The idea is that you can give that your promise is a capability to resolve the deference, and the promise gives you the capability to observe that deference. So you can give these to different people, and they don't even have to like each other, and they're guaranteed to not be able to communicate in any other way than the two objects that you've given. And this leads to all sorts of interesting fun patterns, like you can give the resolver to a bunch of people, and the first person to resolve it wins the race to resolve the thing, and all sorts of other patterns. So more about deferreds. In this box in the middle represents the two-state nature of a promise. It has a before resolution state and a post-resolution state. Before resolution, its contents are a list of people who are interested in the value of the resolution. And those, by people, I mean other promises. And then after the promise has been resolved, it has a value, and that value gets sent to all of the promises that are interested in that value. And the promise and the resolver, and these circles with the arrows on the inside are a sort of representation of a closure. The idea is that if you have a reference coming out of the edge of a circle, that's something that's a property of an object, and an arrow coming from the inside is a property that is enclosed by the object. The idea is that if you give an object to somebody else, they have access to all of the capabilities that are on the surface of that object, but not necessarily they have to use the object to interface all of the references inside of it, so you can protect access to those things. Here's a simple defer. This is an abstraction on the set timeout. It's really simple. The idea is you construct a deferred, you call set timeout, the callback is going to be the resolver, and then you pass the timeout as the second argument, and then you return the promise. So you've got the two parts. The resolve is the resolver, and the promise is the promise. What happens with resolve is it takes one argument. In this case, it's going to resolve to the value of undefined, because set timeout's going to send undefined to it as its first argument. So what this does is it returns a promise that will resolve after whatever time you provide. And the way you observe the resolution of that promise is using a q.when. Q.when was originally in the E programming language. It was a clause. It was more like a try-catch than a try-catch as an expression instead of just like instead of a function call. But in JavaScript, we can use a function call to do this. it has a try clause and a catch clause effectively. The way this works is that you pass a promise in or a value as the argument to when, and if you give it a value, it treats it as a resolved promise. So it will proceed almost immediately, but not in the same turn if you give it a pure value, which means that you can pass into when you can just get a value from somebody else's API, regardless of whether that API is returning you promises or values, which makes for a really clean level of abstraction where you can build a promise-based API in terms of any API at all, and the code is identical. And the first operand you get is a callback. This is the callback that's going to be attached, and it will observe the resolution of the promise. And it receives the fully resolved value as its argument. From there, you have the ability to return a new value. So supposing that you were trying to do a computation of some kind that depends on data that must be acquired asynchronously from somewhere, you use a when block to observe the resolution of that promise, perform your computation with that given value, and then return that value to whoever is asking, to whoever who you are beholden to. So if you're creating an asynchronous API, all you have to do is use, and if you are both producing and consuming an asynchronous API, you never have to use defer. You just use q.when, which will be most of the time. And so you're consuming A and you're producing B. The capital B is what you return to your consumer, and that will be resolved with whatever you return from the inner block. And the neat thing about promises is that they accurately model both returning from a function and throwing exceptions from a function. And they do it in a similar way to the way try-catch works, in that you don't have to pay attention to the exception unless you are interested in the exception. Because if you do not provide a way to observe the rejection, that rejection will be forwarded from your consumer, from your producer to your consumer. The way you do it, to construct a rejection, it's just another promise. Q.reject returns a promise that embodies the knowledge that this promise has been rejected, and you provide as its argument any object you want. Strings are good that tell you why the promise is being rejected. Sometimes it's interesting to provide additional metadata, like, I don't know, stack traces. This is how you do error recovery with promises. The q.when receives as its second argument an error back, and it's not quite an error back because it's responsible for either continuing to resolve the promise or to reject the promise. So the value returned from the error back is going to be either your resolution or your continued rejection. Now, you have an opportunity, if you're rejecting it, to construct a new rejection with more information, or to just use q.reject and pass the reason through, or provide a new value. And if you omit the error back, the rejection reason from your producer will be forwarded to your consumer. Similarly, if you omit the callback, the first argument, the value that you've resolved to will be forwarded to your consumer. So you can also use q.when to just attach error backs and not to not attach callbacks. This is how you use q.when in a compound to do a compound computation. Suppose you're waiting for two different promises to resolve, and these promises are potentially being resolved in parallel. Before you call q.when, you acquire promises for A and B, so they're both off doing their job, and then you use q.when nested to join those promises and then provide a computation based off of those two values. So suppose you're going to a database and also making an HTTP request. You can use this to get your database response in A and your HTTP response in B, perform some computation, generate a new value or another promise. The reason this works is that Q.when in your callback or your airback, you can return another promise to further defer. So if you, which is a pretty common pattern, you're in your callback, you're like, oh, I've made progress, but I'm not done yet. You can then return a promise to continue waiting. And this is super, super elegant. Some more complicated composition problems can be solved using our friend from computer science, reduce. I'm sorry. These things can be really easily wrapped, but I want to show you the guts, because guts are cool. In this particular case, I'm using the reduce function. Who doesn't know how the reduce function works? The reduce function works by taking an array of values, and it tries to aggregate them to a single value using some function. So the trivial example of reduction is a sum. So suppose regardless of the order in which you resolve you combine the values in an array to construct its sum, it will always be the same result, which isn't actually important, but bear with me. So if you take any two values from that and construct the sum, you can take that out and then put the sum in the array, and eventually you'll be reduced down to a single value, and that's what reduce returns. Reduce accepts as its arguments, well, it receives an array, it accepts, and a function that takes the so far accumulated value and also the value of interest at the point, and then you return the new accumulated value. It receives as an optional last argument a basis for the recursion, although it is performed iteratively in the engine. So the way this reduction method works is it's supposing that you have an array of mixed values and promises. What you can do is use this reduce method to wait for all of those promises to be resolved and then perform a computation on the aggregate values. In this case, it's a sum. And the interesting thing about a reduce is it's strictly left to right. So the way progress is going to be made by this particular pattern is supposing that there's a random distribution of resolutions in time. As you go through the game loop in turns, you're going to get resolutions at different times, and then whenever the first two are resolved, you're going to aggregate them, and then whenever the third is resolved, you're going to aggregate it. The fourth is already resolved, but we wait until we have the accumulation of A and B and C to accumulate them. And the neat thing about promises is you can create various reducers for different scenarios. You can create a left to right resolver, you can a left to right reducer, you can do a right to left reducer, you can do an opportunistic reducer, which reduces whenever values become, depending on what the math is, you can reduce out of order. This is, and then, I mean, we're all really super familiar with procedural programming using continue and break and stuff like that. So it's using promises, you do have to get a little clever with solving problems of how to do that kind of thing. This is a solution for a break or a short-circuiting reduction. So the trick is that you want to continue, you only want to continue making computations like searching the file system for directories, which was the case where this came up for me, up to the point where you find the thing of interest, and then you want to cut off the computation. In this case, the way to do this is to construct a chain of callbacks using reduce. And the way this one works is I'm using the generic array method to create an array of functions that perform some computation, which in this case is just returning a letter of the alphabet. And then I reduce from right to left. And the reason for this is that I'm taking the rightmost function and making that the otherwise clause of a choice. So in aggregate, I'm creating essentially a linked list enclosures for functions to call next. And then the function that comes out at the end is the first function I want to call. So if you follow this, the otherwise call, the basis for this is going to be rejection. So if nothing returns a valuable value, I'm going to get a rejection. And for each of the components, I'm going to get a letter of the alphabet, and if the letter of the alphabet is uninteresting to me, I'm going to call the otherwise function that was the accumulated value and reduce. And this models the order of execution This is how you do error recovery. This is, I had this working at one point in Narwhal on Node. Narwhal on Node is not really going forward. I'm in the process of translating all of that work into NPM packages like QUtil, which is done, and QHTTP, which is sort of half done. So I think this one actually works. The way this is an HTTP read retry loop. So we're going to try to make a request several times. There's going to be a constant timeout between tries, and you're going to try a certain number of times before giving up. You can also model exponential backoff with this without too much difficulty at all. So the way this is working is I'm first going to call HTTP read on the URL. This is going to issue an HTTP request and return a promise for the body of the response, which may be rejected if it's not a 200 status. And then I use q.when to wait for that content, and I return it if it's good. If there's an error, and there are no more times left, I reject. But if there are more times, I'm going to further defer using my old delay thing from up top to wait the timeout. And then I'm going to do another HTTP read retry with one fewer times. And this looks recursive, but in an event loop, you actually get a new stack each time you're on the body of a q.when. Let me tell you about some of the promises of q.when. Invariants, not promises, pardon. Don't want to load my vocabulary too much. Q.when guarantees that the inner callbacks are going to be called in a future turn of the event loop. This is to prevent confusion, logical confusion with, it permits you to do in one turn of the event loop to set up a whole bunch of things to happen in the future, and guarantees that all of the values in your lexical scope are going to be preserved for the duration of your turn. You are in complete control of your values. It also guarantees that the q.when function guarantees that your callback and errorback are only ever going to be called once, and only one of them will be called. So this is really resilient against many, many hazards and malice even. This is how you implement an HTTP request via XHR using promises. I think everybody's done XHR at this point directly. We construct a response deferral. We construct a raw HTTP request. We open it, we set up the onReady state change handler, and we resolve with the response text if it works. We resolve with a rejection if it does not. And we return the promise for the value and initiate the HTTP request. There's a little thing in here with the timeout equals set and set timeout. That adds the set timeout semantics, and I think that one line really expresses the awesomeness of this API. In one line, I have implemented timeouts, and because the promises guarantee that the first person to resolve the promise wins, if it's rejected, it's rejected. Even if the HTTP request eventually manages to give you some data, the timeout's out. Your promise will never be modified again. This is a demonstration of how promises can be used as currency. In the way that money has really freed us up from the barter of things, promises have the ability to free us up from bartering. Are we close? Okay. So we're bartering promises. So if you have symmetric APIs where responses and requests have a certain degree of symmetry, these things can be passed around really easily. So this is what happens here is that if you're issuing via the request API a request, and the request is a promise and it returns a promise, and this is completely asynchronous but looks very, very synchronous. I'm going to just skip this. This is an HTTP queue and promises. There's a really cool promise implementation. There's a really cool promise trick you can do where you can create a queue of promises, and you can actually pop things off of the queue before they're resolved, and it just constructs this. It's really cool. Look into it. This is the implementation. It works in browsers. It works in Node. It works on Narwhal. It's really small. There's no reason not to use it. It really simplifies complicated asynchronous code both on the server and the client. I really encourage its use. You can get it on GitHub. with my alliterative name and Q as the project name. You can also npm install Q. It's there. Then I was going to show you some stuff from a utility library. I created a Q util. It's in progress. This does shallow resolution of an array. So it simplifies. You don't have to use reduce. You can just use the shallow resolver to take an array of promises and get a promise for an array instead. And this can do a deep resolution, which if you have a whole tree of objects that may include promises. And shameless plug, since May I've been making a map of Middle Earth. It's like Google Maps. It's really cool. And because it wasn't awesome enough, I also did it in Elvish. And have a good day.